So first of all, let's talk about this next week's quiz, which is going to be on Tuesday, period 10. Same thing like we did with quiz 1. Yeah, I think I should share with you. I don't know if you have that information already, but I think I received an email some time ago confirming the room, I think. I have to double check. I will send an announcement about it. However, the topics that are going to be covered are week 7, 10, and 11, which means these weeks over here: sequence transformations, divisibility, and integer representations and algorithms. This is what we're going to see today, inshallah. Yeah, some people were, I received just one email about something about, I think, the title here of the chapter. I see the chapter mentions matrices, but we don't do any matrices. Well, yeah, because we don't cover all the sections of each chapter. And we don't even cover each chapter because you can see we jumped from 2 to 3 to from 2 to 4. And even number 4, it says number theory and cryptography. That's the name of the title of the chapter. But we focus on the sections. All right. So we're not going to be talking about any cryptography. However, the chapter 4 is about number theory and cryptography. So anyways, focus on what is written here in week 7, and when we mention week 7, so that means this is 2.4, 4.1, and 4.2. This is what is going to be included. And then later on, after in the same time, inshallah, we will be talking about 4.3, 4.4. Very briefly, this 4.4. I think someone said something. Period 10. Yeah, not period 10. Period 4. I said 10, sorry. Yeah, I mean period 4, 10 a.m. There will be the same questions as in the reviews, yes. The questions are going to be from the same pools. That's what I mean, from the same pools, yeah. That means the more review you do, the better you're going to be. Of course, the number of questions are going to be for half an hour, so expect the same number of questions. Something similar to what we did in quiz 1. I think it was 40 questions for 10 minutes, for 30 minutes. Which is more than enough. Based on the statistics of last time, many people finished quite within 20, 15, 20, 25 minutes. So, yeah, this being said, I also uploaded the 4.2 and then the updated 4.2, because I just found that maybe on a section required a little bit of more information, which I just added about it, and I corrected some mistakes in the first slides. Yeah, something like that. So if you do have any questions from what we did last time, this is a good time. If not, we'll start immediately with this here. Inshallah, we will stop before the Maghrib time, because I think this will cover that. I mean, the number theory is not very heavy, so we will be most likely finishing by Maghrib time, inshallah. I will get the mini test just before Maghrib, and then inshallah, this is the plan. Okay, so today what we're going to be talking about is representations of integers and some algorithms for integer operations. Well, basically how to do some additions and multiplications. Well, we know how to do additions and multiplications for like the numbers that we know, like these are called decimal numbers. Well, what we're going to be looking at is different bases. Now, we know, most likely you do know for sure, that there's this decimal numbers, which are the numbers that we use, and then there is the binary, because these are the numbers that you use on the computer. However, there are other actually base systems that we use, and mostly you see them in the calculator when you use the scientific calculator. Is it scientific? No, maybe the programmer calculator, yeah. So in the programmer's calculator, you're going to see this hex for hexadecimal. The decimal is the number that we use. The octal are the octal, that means 8, maximum 8 digits. The binary are like zeros and ones, right? Now, if you notice, when we do this, look at these calculators. Now, for the decimal, we have all the possible digits. from 0 to 9, which makes them 10. That's where decimal comes from 10. And now octal, that's 8. That means the maximum is going to be 7 from 0 to 7. Binary, 2, that means 0 and 1. And hexadecimal is actually beyond. It has the from 0 to 9 plus A, B, C, D, E, F. That's where we stop. Okay, so we'll talk more about these and how to do also additions on them, how to convert from one to another. And this is the topic of this lecture. So without any more delays, let's just bring this back how it is, and then we will talk about this. Yeah. So the thing is, we're going to be talking about, let's say, the binary, the octal, and hexadecimal, and then the general format on how to use them. Now, before going into the slides, I just would like to give you some kind of general idea about what we're going to be talking about, and just to know what we're going to be doing. Now, we know how to count, right? When we count how from 1 to 2 to 10 to 25 to 100, whatever, I just would like you to realize actually what we are actually doing, because we're going to be doing the same thing when we're going to be counting in binary or in octal or in hexadecimal. It's the same logic, the same algorithm, same way we do the things, except that the number of not the number of characters, let's say, or the number of digits that we're going to be using are different from one base to another. So these are called bases, like the binary, the octal, and the hexadecimal and decimal. So let's have a look. Now let's count normally. How do? We count from 0, right? So we start from 0, 1, 2, until we continue up to the last digit that we have, which is 9. And then what happens when we run out of digits and we want to count more? Well, we start again from 0. So we go back to 0, and then we remember that we started again. And then we continue 11, 12, which is this, again, this 0, 1, 2, 3. But we always remember that we repeated the process of counting from 0 to 9. And then we're going to, again, do the same. To go down. So we're going to keep doing the same until 1, 2, 3. That means 13, 14, 15, until we reach 18 and then 19. And when we run out again of digits from 0 to 9, what we do? Well, we reset, go back to 0, and then we remember that we need to go back to 0, which means we increment the left side. Now, we can just maybe realize that we did the same here, because this could be represented as 0, 0, 0, 1, 0, 2. That's the same thing until 0, 9. And then when we run out of digits and we have to restart, we just need to remember that we restarted, so we just add +1 here and then reset it to be 0. So that's what we do in the calculations. And we keep doing this until we reach this 20, 21, 22, etc. until, for example, 98, 99. And then when we reach 99, well, we run out of numbers again, so we have to reset. So we need to reset them back to 0. And then when we reset it back to 0, I need to increment this one. Well, this one, we run out again. So we reset again, and then we remember that we reset it to different positions, etc. Anyways, now we know how to count, but this process, this is how this works. We always use all the digits that we have. When we run out of digits, we reset, and then we remember that we started again from the 0. Now let's compare that, and because you know that binaries are just zeros and ones, now how do we count in 0 and 1? Now the number of digits that we have in a binary are only 2, while here there are 10. That means this resetting is going to happen more often. So I start with 0, and then I have 1. Then, okay, I'm done. I have to reset. So this is, I'm going to maybe just let me do this differently. Oh, okay. This thing is not going to work. All right. So what I'm going to do is I am going to maybe just put the numbers, the decimal numbers, 1, 2, let's start with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and let's go up to 15 just for fun, because 10, and then I have 11, 12, 13, 14, 15. Okay, so this is decimal. Now in binary, we start also from 0, right, which is the 0. The equivalent of 1 is 1, but then I run out, so I have to remember that I have to reset. So I reset and I put a 1, 1, 0. So this is the 2. Now 3 means I can increment, so that's the 3. And then I run out of zeros. I'm just going to reset, and I have to increment this one or run out of digits, so I have to reset, and this is how we count. We just start by incrementing the right side. When I'm running out of digits, well, I have to go back to 0, and then remember the one that is next to it, I have to increment it by 1. And this is how we count in binary. So this is 4, this is 5, this is 6, this is 7, and 8 is going to be 0, 0, 0, and then 1. And there you go again, and you keep going. So this is how we count in binary. Now in octal, it's kind of similar, except that I have the digits from 1, 0, 1, 2 until 7, which means I'm going to start with 0, 1, 2, 3, 4, 5, 6, 7, and then I run out, so start again. Now notice that this is 10, like this looks like 10, but because I'm in a binary, this 10 is different from this 10, which is different from the other 10 that we used to do in the decimal. Now how to distinguish between these? So we are going to represent the 10 like this. This means the decimal. If I want it to be a different base, I'm just going to make it, for example, 2. That means this is a binary 10. This is 1, 0. And if I put this 1, 0 here as octal, that's 8. So octal actually is also for 8. And that's the idea. And if it's actually hexadecimal, then it's going to be 4 out of 16. Now the hexadecimal, let me just talk about it. For hexadecimal, what we do is that we start from 0 to 1, 2, 3, 4, 5, 6, 7, 8, 9. But actually we want to put 10, but this 10 might be confused by something else. We want something to be a different digit. So that's why we actually are going to use some letters. A, B, C, D, E, and F. Well, this is, A is actually the equivalent of 10 in decimal, B is 11, this is 12, this is 13, and this is 14, and this one is 15. And we stop in here. So which means now, if I'd like to count in decimal, so I'm just going to do 0, sorry, in hexadecimal, I'm going to count 0, 1, 2, etc. until F, and then back to 0. But this 0 here in hexadecimal is not 10, because this is in the base of 16. Now, okay, we'll talk about now. Let's go back into the some of the theoretical parts, so I can represent that. So you get the point now. The idea is that I'm going to represent the same integers, except that I'm going to use different ways how to represent them in binary, in decimal, in octal, in hexadecimal, and then we will try to find some ways and to how to convert between each one of them. Okay, and why are we looking at these? I mean, decimal, basically this is how we count in our daily life. Binary and octal, binary and octal, why are we using those? Well, basically because these are actually very much used in computers, in computer science. So octal is out of 8, right? And then this is a byte has 8 bits, right? So, and then we have also, see this hexadecimal, which is base 16, which is like, instead of 8, it's twice, it's 16. So they're all something related to this binary thing. But anyways, that's the idea. So now the base is what we're going to be representing. So if I give you a number, this 527, and I tell you this is base 8, you understand, first of all, that this is not 527. So this is a 527 that, okay, how does it convert to decimal? We will learn how to do that. But if I give you, for example, something that says like 293 and I tell you this is octal, of course you're going to tell me no, there's a problem, because we said in octal the maximum can be 7. I cannot have 8, I cannot have 9. So this is not an octal. This is wrong, a wrong way to write this. Similarly, if I tell you that this is a binary number and then I do something like this and tell you this is a binary, of course you're going to tell me no, it's not possible. We cannot have 3 as a binary. We are either 0 or 1. So just be careful about those. So I'm back. Let's just now focus more on how to represent those numbers and how they are represented, and how this basic representation that actually we know but we don't pay attention too much to it is going to help us do these conversions. Now let's look at this theorem. I mean, this looks kind of complicated, but it's fairly easy. So let's say I'm just going to say that b is an integer greater than 1. b in this case, this is our base. Now what is the base? Well, we said the base is either this decimal, octal, binary, or 16. This is the hexadecimal. So this can actually apply to any integer, but these are the general ones that we use, right? But I can have a base of 3, I can have a base of 5, if my base is 5, which if I tell you base is 5, that means the digits are going to be 0, 1, 2, 3, 4. That's all the possible digits. So theoretically speaking, we can use any base that we want. However, the most bases that we're going to be using are either decimal, binary, octal, or hexadecimal. So this here tells you that any number that you have, let's say for example I have 1527. This is my n. So n is this number. That means I can have this number, any number that I have, can be represented in this format, where actually it's a number multiplied by the base to the power of some k. Now, basically what we are going to do is, remember, this is base of 10, that means this is the power of position 0, position 1, position 2, and position 3. Now, this represents 1000, right? Which is 1 multiplied by 10 to the power of 3. This is 1000 plus, because we have these pluses over here. Now, what's the number here? 500. That means 5 multiplied by 10 to the power of 2. That's 500. Plus 27, that is plus 2 to the power of 10. Multiplied by 10, which is my base, to the power of 1. Plus 7 multiplied by 10 to the power of 0. Now, 10 to the power of 0 is going to give me 1, right? Anything to the power of 0 is going to give me 1. So that's why, actually, this is how we read it, 1527. So this is for the thousands, this is for the hundreds, this is for the tens, and this is for the units. So that's basically what this theorem says, is that you can represent any number into this format, uniquely into this format. So that's pretty much what it means. So you can have, like, now if we apply this to the binary, now for the binary something similar. Now what is this binary representation of this? Well, that means this is position 0, position 1, position 2, position 3, 4, 5, 6, 7, and 8. Now that means what we have is 1, this one over here, multiplied by 2, this is our base, to the power of 8, plus 0 multiplied by 2 to the power of 7, plus, this is the 0, this then plus 1 multiplied by 2 to the power of 6, and then 0 multiplied by 2 to the power of 5, and then I keep going until, okay, this is 5, this is 4, that means plus 1, 2 power 4, plus, what is it, 3, that means 1, 2 to the power of 3, plus 1 to the 2 to the power of 2, plus 1, 2 to the power of 1, plus 1, 2 to the power of 0. And then I can calculate this, and this is going to give me the actual conversion of how this binary number is going to be in the decimal equivalent. What is decimal equivalent? So I'll just convert it using this format, because every representation of a number, regardless of its base, it's going to be equal to this. So this thing is equal to that. So the idea is we just start, remember that's the only thing you have to remember, is we start from 0 from the right side, and then 1, 2, 3, 4, 5, 6, 7, and then we go and keep going. If the number is much longer, we're just going to go until we find it, and then we calculate. 2 to the power of 8, what is it? Was it equal to? 2 to the power of 0, this is equal to 1. This is 2, this is 4, this is 8, this is 16, this is 32, this is 64, this is 128, and this is 256. I'll just take this one, multiply each one by 2, 2, 2, and that's how I can get to this one. So it's 256 plus this one is 0, that means it's gone, plus 64, and then 32 is gone, that means plus 16, and then plus 8, plus 4, and 2, and 1. That's a lot of pluses. So if I just sum these, it is going to give me 351. If you would like to make sure, just we can do the calculations. 6 plus 4, that's 10. That means here 6 plus 6, that's 12. That means 320, these two. Plus 16, that means it's 336. Plus, I mean, I can just calculate these. These are all 15, right? Because this is 8 plus 2, that's 10. Plus 4, that's 14. Plus 1, that's 15. So I'm just going to add this 15 to this, and it's going to give me 1, 5, and 3, which is this number over here. So this representation is going to allow us to actually evaluate what any number in any base can be represented in decimal. And that's the same logic. If you would like to apply this here, let me just maybe do the, let me save this. If I just copy this thing. So let's go back. Okay, I lost it. I can get it back here. Okay, so what this is going to be equal to, well, no problem. We're just going to apply the same rules. Okay, so come on. So what are those rules? Where is this? Okay, so this is equal to, now this is going to be position 0, 1. Okay, let me zoom in. It will be better if I do zoom in. Okay, so this is position 0, position 1, position 2, position 3. That means this thing is going to be equal to 2 times, sorry, not 2, 7 times what? 8, because we are base 8 to the power of 3, plus 0 times 8 square, plus 1 times 8 to the power of 1, and then plus 6 times 8 to the power 0, which is, this is going to be just 6, because this is equal to 1. This is 1, so this whole thing is 6. This is 8 to the power of 1, that's 1, times this is going to be 8, so you have this is going to be 0. And then we need to calculate this. Well, we know that this is 8. 8 times 8, that's 64, right? 64 times 8. 8 times 4, that means 32. 8 times 6, which is going to be okay, am I? The papers, we'll talk about them later at the end. What is the point of counting from the right, not left? What is the point of counting? I don't understand the question. You're talking about what here, this counting over here? This is not actually the counting. I'm just giving like a position. This is the position 0, position 1, position 2, position 3. And this is how these work, because if I tell you like this is 7,016 in terms of decimal, like decimal, how do you say this is 7,000? Why do you say 1,000? Well, because this is 7, 10 to the power of 3. 3, 10 to the power of 3, this is 1,000. So you said 7,000. 0 hundreds, but we're not going to say that. And then we have 16, which is 1 decimal, 1 times 10 power of 1, plus 6 times 10 to the power of 0. This is how this actually works. This is how we do the calculations. This is how we represent numbers. It's just like, this is how we need to do it. These numbers are, these numbers here, 0, 1, 2, 3, these are the position of the digits. The 6 is at the position 0, 1 is at the position 1, 0 at position 2, and so on and so on. Okay, I wanted to calculate 8 times 6. Isn't that 42? I think so, right? I'm not sure. I'm having a blank now. 8 times 6. Oh, it's 48. So it's 48 actually, plus the 3 that I was saving there. That means it's going to be 51. So this is going to be this 51. And then if I multiply 7 by this 512, because this whole thing is calculating 8 to the power of 3, 8 cube. So it means 8 times 8 times 8. That's 512. And then if I multiply it by 7, this is going to be this number over here. So that means this is going to be 3,584. Then I need to add 8 to it and then 6 to it. Well, 8 plus 6, that's equal to 14. So I just need to add 14 to here. This is 8. This is 9, 5, 3. So this here is equal to that. If I just put the number like this without any referring to base, by default it's base 10, because that's what we use by default. So I don't have to do that, but if you do it, that's correct. That's not a mistake. If you just say that this is equivalent to this or this is equal to that, that's actually okay. So let's go back and compare what was mentioned here, and as 3598, and this is what we got, 3598. Now it's even going to be take us some more time if we need to do this now in the, sorry, where is it? The hexadecimal. Let's do that because it's we need to know how to do this. Well, basically C is going to be the same thing. Now we can again represent these, and where do we get this? Again, this is the same format that we were talking about. This is position 0, position 1, 2, 3, and 4. Now the only thing also that we need to take care of is that what is the value of A, what is the value of B, what is the value of C and D and E and F. Now remember, this is, we said that this is 10, this is 11, this is 12, 13, 14, and then 15. So which means when I have 2 to the position in position 4, that means 2 times 16 to the power of 4. And then I have A. I'm not going to write A times 16 to the power of 3, because what is A? Well, it's 10. A is 10, so I'm just going to write just this A to be 10 here to the power of times 16 to the cube. Plus E. Okay, what is E? E is 14. That's why I'm going to write this is just for representation. It's going to be easy for you to find out. E is the 14. And then 0 is 0. And then I have B. What is B? B is 11, so this is the B. Now this is 16 to the power of 1. That's why they just put 16, and this is actually times multiplied by 16 to the power of 0, because this is multiplied by 1, which does not do anything. We just can add something like that. So that's the idea. That's why I wanted to start from 0 to know that there is a 0. and it's easy for you to memorize that this is, to understand that there is a 0, and that 0 does not affect the multiplication, because 0 to the power of anything, 0 is a number to the power of 0 is going to be always 1. Any number is going to be power 0, going to give you 1. So 1 multiplied by anything, it does not change anything into the calculation. So that's why this was omitted and just put like this. So now all we have to do is use the calculator and then do this, because I mean we can just this 16 plus 16, that's 32, and 32 plus 32, that's 64. That means this is 64 times 2, and this is 10 times 16 times 2, that means 32 times 16. Oh no, I made a mistake, I said 64. That's not 64, it's 32 times 32. Yes, 32 times 32 times, which is 32 square. What is 32 square? Times 32. Well, I can just calculate it as 4. Well, I'll just use calculator so we don't lose much time, because I'm not relying too much on my brain, just in case I'm not saying some mistakes. So 1024. So 2 times 1024 plus 10, 16 times 16 times 16. I did something wrong again. What did I do? 16 times 16 times 16 times 16. What did I say this? 1024. This is not 1024. This is 65,500. 65,536. See, that's why I did not trust my mental calculations. Somebody just wrote something. Let me just write C. Is the answer the overall? Yeah, okay. We can just do this multiplied by 2. This is going to be the first. This is what you're referring to. So this times 2 is going to be this, this number, and then I have to do the same for the rest. So anyways, 1 1 3 1 0 7 2. And actually, this reminded me too. This is going to actually, what I need to do is to do the calculations, but if I want also to do conversion, I'm going just to check. I mean, I want to do the calculation so you know how to do it manually, even if you don't have access to this type of calculators. But if I have a calculator, see, I can mention that in hexadecimal, now that means I'm going to input a number in hexadecimal. In this case, I'm going to input this number, which is 2, A, E, 0, and B. Now notice this thing, it gives me right away what's its value in decimal, in octal, and in binary as well. So it converts that number in from hexadecimal to any other ones. And similarly, if I choose like this number, it just gives me this number and it converts it to all the other, common ones for the programmer. So if I want to check, all I have to do, for example, if I want to know that if I did something right, all I have to do is to write this, and then it's going to give me the answer. But I want you to be able to know how to find the answer, and to be able to know how to find the answer is by following this rule that we just saw, which is you have any number is the equivalent of some number times the base to the power of some k. So this is the k is how many numbers there are. This is A0, A1, A2. Notice that A0, because it's B, that's exactly similar to write B. This is times B to the power of 0. This is similar, just say times B to the power of 1, and then etc. until we reach the last digit that I have. And that's how I can calculate and get in the number, any number that I have. So as you can see, this is the equivalent of that. Now, if I'd like to do the conversion, now to do the conversion from one base to another, then this way to actually divide, just to divide by the base, and then we just look at the remainder, what remains, and each one of the digits that remains, and we just is going to be part of the answer. I think this can be a little bit confusing. That's why let me just show up with an example. Now, let's say I would like to find the octal expansion of this, which means the equivalent of this number in octal. Now, how to do that? What I'm going to do is I'm going to take this number 1, 2, 3, 4, 5 and divide it by 8. Now this 123.5, when I divide it by 8, I'm going to divide and not just get only the, I mean, this is normally it's going to, maybe it's going to give me like the decimal if I divide by 5. Why did I divide by 5? 1, 2, 3, 4, 5, divide by 8. I don't know what's happening to me today. 1, 2, 3, 4, 5, divide by 8. So this gives me this number, which means actually it divides it properly and the remainder is 0. So is it? No, it doesn't seem like, because it says like it's 1. Well, maybe because this programmer actually divides it without leaving any this is doesn't keep the track of the division. So let's say I'm having this 1, 2, 3, 4, 5 divided by 8. 1, 2, 3, 4, 5 divide by 8. See, there you go. Now it gives me something. So it's 1543 point something. Now what I need to do is, okay, let me just go back to this place. I have 1, 2, 3, 4, 5. This is in octal. Or is it in decimal? This is in decimal. So this is in decimal. I want to find what is the octal value of that. So what I need to do is to get this number and I divide it by 8. That means this is going to be something. Maybe this is like a quotient, some number multiplied by 8 plus whatever is remaining. So now I just need to find what is the quotient. Sometimes what is remaining is 0, but for us, what I need to do is, if I need to do this, that means 1543, this is what I need to do, but I have plus something. So this is equal to 1543 times 8 plus what? And how can I find out plus what? Well, all I have to do is take this minus 1543. Just need to be careful. So this multiplied by 8, it is going to give me how many? So because I divide by 8, right? So the remainder is what is divided by 8. I just multiply by 8, so I can get that 1. So this is going to give me the 1 here. Now remember, we don't do that with the programmer's calculator because this is going to give us something not right. Okay, now once I have this, now this 1 is going to be part of the answer. We'll see how. Because I need to repeat this division, I'm going to take again this number, 1543, and I'm going to find out it's divided by, if I divide by 8, it's going to be what? So I'm just going to say 1543 divided by 8. This is going to be 192 multiplied by 8 plus something. So how do I know what's that something? Well, I need to just remove this 192. So I just have this whatever was after the decimal point, and then multiply this by 8 is going to give me actually what it is. So this is going to be the 7. Okay, so this 7, I'm going to use it. So I'm going to repeat this until this number becomes actually 0. So then 192 is going to be equal something multiplied by 8 plus what? Okay, let's find out. 192 divided by 8 is going to give me 24. That means this is actually 24 multiplied by 8 plus 0. Okay, what is 24? Is going to be, again, I'm going to remember this one. And what is 24 is, again, divided by 8. So 24 divided by 8 is going to be 2 plus something. Oh, no, 3. Right? Divide by 8. 3, and then this remainder is 0. And this is going to be 0, so another 0 here. And then I need to continue again. So this is going to be, again, 3 is equal to 0 divided by 8 plus 3. And when I reach the 0, this is where I stop. Now, what do I do with these numbers? The remainders of those numbers, these are actually the ones that are going to constitute my number in octal. So remember, we said that this is going to be representing something. What does it represent? Well, it represents this. So what am I starting with? So this 1, 2, 3, 4, 5 in decimal is equal to, and let me just give me some space. So it's going to be this 1 is going to be the one on the right, and then 7, 0, 0, and 3. This is going to be the octal representation 1, 2, 3, 4, 5. Again, how to check? We can check by going to this programmer and type in the number 1, 2, 3, 4, 5, and I can see that this is an octal. See this octal? This is what it's going to be, 30071 in octal. So how to find it? So when I would like to move from one base to another, all I have to do is to divide by that base, and it will tell me what it is. Okay, let's just again apply the same logic to the numbers. Let's say 1, 2, 3, 4, 5 again. Okay, what is it going to be in binary? In binary. So it's going to be in X in binary. What is the number? I'm trying to find it in binary. So what to do? I'm just going to do the same logic. 1, 2, 3, 4, 5 is going to be something multiplied by 2 plus some rest. Obviously this is not going to be, this is not even, so it's going to be plus 1. So I just need to find out. Okay, 1, 2, 3, 4, 5 divided by 2. And just again, let's go back. No, don't divide here in the programmer because it doesn't give us the 1, 2, 3, 4, 5 divided by 2. So it's going to be 6172.5. 6172 multiplied by 2 and plus 1. And now this one is going to be the one that I'm going to be building my answer with. And then here again, I'm just going to say 6172 is going to be equal to what is going to be divided by 2. So this is going to be the remainder of 0. So minus 0.5 because I'm just going to remove it. Divide by 2. So 3086 multiplied by 2 plus 0 because I know it's going to be 0. And that's the second digit there. Then keep repeating. 3086 equals something multiplied by 2. I think this is 1543 plus 0. Again, this 0 is going to be used. And then 1543 is going to be equal to, let's say this is 715. It's 750 plus 20. That's 71 times 2. Am I right? Can you double check if I didn't make a mistake? If I make a mistake, just correct me. If I don't make mistakes, just say nothing. So I don't know. I don't get the notification. Okay, so I think this is going to be correct because 771. Then 771 is going to be like this divided by 2, 350, and then 35, so 85, 350, 385 times 2 plus 1, and then 385. So I'm counting on you to correct me if I make a mistake. This is going to be 150 plus 40, 150 plus 40, so that means 192 times 2 plus 1, and then 192 is going to be equal to, okay, so this is going to be plus 0 for sure, and times 2, what is it? So 190, 180, that's 90, that's 95, 96, and then 96, that's a long number, long binary, I mean. 96 is going to be 45 plus 3, that's 48, times 2 plus 0. What happened? Okay, I'm getting closer to the limit of the screen. All right. And keep going. 48 is equal to, that's 24 times 2 plus 0, and then 24 is equal to 12 times 2 plus 0, and then 12 is equal to 6 times 2 plus 0, and then 6 is going to be 3 times 2 plus 0, and finally the 3 is going to be 1 times 2 plus 0, sorry, plus 1, and finally 1 is equal to 0 times 2 plus 1, and this is when I stop, only when I reach this to become 0, so there's no point, because actually even if you want to continue, this is going to be 0 is equal to 0 times 2 plus 0, so you just have the zeros at the left side, and as you can see, if you have 0 1 1 0 0, if you keep adding more zeros to the left, it doesn't make any difference. That doesn't change the number what it is, so that's why we stop at 0. Now if we'd like to get the number, okay, so what is the number? The number is going to be 1 1, so let's say 1 1 0. Okay, so I'm just going to strike it so I know I don't get lost, and then 1 2 3 4 5 zeros, 1 2 3 no, 1 2 3 4 5 zeros, and then 1 1 1 0 0 1. 1 1 1 0 0 1. That's a very long number. Now, when we represent these binary numbers, it's very hard if I just represent them like this. So what generally I should do, every 4, I just going to combine them and leave some space for the other 4. So for example, take this one, this is 4, and then I have 1 1 0 0. So that means these 2, these 4s, and then I'm just going to represent these 4s. That means 0 0 0 0, and then the last 1 1. I can put also 0 0, doesn't make any difference, but yeah, it is not needed. So this is the binary representation of this 1 2 3 4 5. Let's double check that. Let's go to the programmer, and we set in decimal 1 2 3 4 5, and we can see that this is the double zeros here, 1 1, and then 4 zeros, and then 0 0 1 1 0 0 1 1. It's right here, I can see it, and then this is 1 0 0 1. Alhamdulillah, we did not make any mistake. So you get the point. Now the idea is I'd like to convert from one to another. This is what I need to do. Now if I'd like to convert to 16, basically from this to 16 to hexadecimal, what I have to do is to take this number, divide it by 16, and then take this number again and divide it by 16. That means this is going to be the 10. But what is 10? I cannot use 10, of course. Remember, every time we have 10 11 12, this is going to be A B C D, etc. So 10 is A in this case. So and then okay, and then take this number again, divide by 16, it gives me something plus something. What is this? 14. A B C D E, right? And then I have again take this number and then divide by 16. I got this 3, which stays at 3, and then I have this number and then divided by 16, and it gives me this 11, which is B. And then I have this 11 divided by 16, it gives me 0 plus, sorry, not 11, this 2. You divide by 16, 0 plus 2, and that's going to be the number, which is going to be 2B, 3E, A. I'm just going here. This 2B, 3E, A, right? 2B, 3E, A. That's in the 16. And that's how we do these conversions. So basically nothing, and we can apply to other things as well. So that's pretty much it. This is just a table summarizing all the digits, the decimals, from 0 to 15, because hexadecimals goes from A, B, C till F. Now in octal, as you can see, once I reach 7, I have to start again from 1 0, 1 1, 1 2, etc. So that's why this is represented like that. And the binary is 0 1 1 1 0 1 1 1 0 0 1 0 0 1 1 1 0 1 1 1, and then back to all of them 0 0 0 and then 1, and then this is back again to the same. And that's how we count on these ones. Now the other thing is, okay, how to move between, like maybe from the octal and hexadecimal from the binary. Now this is actually why there are actually this way how to do this. If I'd like to convert, for example, to this into octal. Now this is a binary number into octal, that means out of 8. So how do we do this? Because the way how the 8 works is that we just need to represent, to get to the octal. Octal is 8. Now this is a binary. We'd like to reach the 8 out of 8. That means binary, we know that this is something to the power of something. If it was 8, that means it should be power of 3. If it was hexadecimal, that means 16. This is 2 to the power of 4. Now why am I saying that? Because you need to pay attention to these 3. For example, if I'd like to convert a binary to an octal, I'm going to use the fact that octal is 8, which is 2 to the power of 3, to know that I need to group now these binary digits into blocks of 3s. Now you see they're represented in blocks of 4s, but I'm going to present them in block of 3s. Now each one of them, this is going to be the first block, and another block, and another block, and this is another block, and that's this one, it's only 2s, so that means on the left side is going to be 0. And then what do I do with those? Now these ones are going to be, and so these blocks, I'm just going to convert these ones to what number it is going to be, and the in the equivalent number from, let's say, from this 0, 1, 1. Okay, we say 0, 1, 1. What is 0, 1, 1? How can I convert 0, 1, 1? This is going to be actually 0, 2 to the power of 3 plus 1 times 2 to the power of 2. Is that? No, that's not the thing, because there are only 3. That means this is actually not right. I'm just saying something wrong. That means this, actually this 0, 0, 1, 1, sorry. It's okay, it's easy for me to go back to here. That's where I can erase and do whatever I want. So we said 0, 0, 1, 1. This is equivalent in 1. Okay, this is in binary. How this is going to be equivalent to? So this is position 0, 1, and 2, right? So that means this is 0 times 2 to the power of 2 plus 1 times 2 to the power of 1 plus 1 times 2 to the power of 0, which is going to be, this is equal to 1, this is 2, and this is 0. 2 plus 1 plus 0 is going to give me 3. So that means what I'm going to do now is that this here, this 0, 1, 1, this is 3. Okay, I'm just going to now do the same thing with this 1, 1, 1. Okay, what is 1, 1, 1? 1, 1, 1, that means it's going to be 2 to the power of 2, which is, I'm just going to make it 4 plus 2 plus 1, because we say that this is going to be 1, this is going to be 2, and this is going to be 4, right? Because it's 2 to the power of 2 to the power of 1 to the power of 0. It's going to give me these numbers. So 1, 1, 1, that means 4 plus 2 plus 1. That means this is going to be 7. What am I doing with this? This is going to be the 7. And then take the next 3. 0, 1, 0. Okay, 0, 1, 0. This is going to be 2. Because this is 1, 2, and 4. So it's going to be no 1s, no 4s, just 1, 2. So that's going to be 2. That's a weird 7. This is 2. And continue from the left to the right. And this is again 1, 1, 1. It's going to give me another 7. And 1, 1, 1, 0, 0. What is this 1, 0, 0? That means it's going to be 4. Of course, this is now in binary. So this is 1, 2, 4. So it's going to give me 4. So this is 4. Which means from binary, I converted this to the number 37274 into the octal. Now if I want to do the same, if I want to do the same now, this same number, if I want to convert it to hexadecimal, well, hexadecimal is 16, which is 2 to the power of 4. which means I need to group this by 4. So grouping them by 4 is going to lead to what kind of blocks? So here, this is going to be the first 4, the second 4, the third one, and here I have only 2. I can just put 0, 0, it's not going to disturb me. And now by grouping them like this is going to be the equivalent, the number of that. So and similarly, this is going to be like, this is 2, sorry, not 2, this is okay, give it 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and 2 to the power of 3, which is basically, this is going to be the numbers 1, 2, 4, like we did before, and then the new number is going to be 8. So when I see this one here, that means 0, 8, 0, 4, but just 1, 2, and 1, 1, 1. That means this is going to be 3. Okay, I have 4 here. That means I have 1, 8, 8 plus 4 plus 2. 8 plus 2, that's going to be 14. What is 14? Well, there's no 14. I need to convert this to, okay, A is 10, B 11, C 12, D 13, E 14, and F is a 15. So now this means this is E. And then I have this again, that means 8 plus 4, that's 12, plus 1, that's 13, that's the D. And then this is 8 plus 4, that's 12, that means C. Which means that this number in binary is equivalent to 3EDC in hexadecimal. And that's what we have. Yes, that's what we have here. So that's the idea behind that. Okay. Any questions so far? I think I just provided here a different way how to do the exact same thing, but it's again the same logic. When we work with octal, that means it's 2 to the power of 3, and that's why we have this 1, 2, and 4. That means this is 2 to the power of 0 is going to be 1, 2 to the power of 1 is going to be 2, 2 to the power of 3 is going to be, 2 to the power of 2 is going to be this 4, and we just group the numbers that we would like to convert into a number of 3's from the right side, and then we can evaluate those from the 3's. As you can see, this now they are kind of just rewritten in a way that they are easy to find the grouping, and then you just count what is this value, convert this to decimal, and it's going to give us these digits, and these are representing the number. Similar to the hexadecimal, that's the same logic. Is that okay? I don't know if everybody's fine. Okay. All right. Now, the last thing we're going to be talking about is two things. Now, how do we do these additions of like these numbers, like for example the binary, how we do those additions, and multiplication. And basically the idea is that, okay, we know how to add to decimal numbers. How to add now to binary numbers? Well, it's all the same logic, the same thing. Let's say I'm just going to use some different examples, and then we look at the other examples. Let's say I have this number 1001 and then 110. That means it can put like a 0, and then I would like to do the plus. So what this is going to be resulting in, well, similarly, 1 plus 0, that's going to be 1. 1 plus 0, that's going to be 1. 1 plus 0, that's going to be 1. And then 1 plus 0 is going to be 1. So not a big deal. But what if now this is going to be kind of different if we have something now different. Let's say I have this 1 over here. And now this is going to be some, even, let's see, okay, let me put 1 here, 1, 0, 1, for example. Now if I'd like to add these two now, 1 plus 1, I cannot say it's 2, because we said, again, binary means either 0 is 1. So I'm just going to 2, that means it's actually 1, 0. I'm going to put 0 on, remember that I started, so I'm just going to now send that 1 to be added to this one as well. So now we have 1 plus 0 plus 1, that means 2. Okay, back to 0, and then put 1 here. Okay, so this is going to be 1 plus 0 plus 0, that's going to be 1. Then have 1 plus 1, well, it's 0, and then I carry out the 1, and then 1, there's nothing here, so it's going to be 1 here. So this is the result of the calculation, basically similar to what we used to do, except that I need to pay attention that I cannot use more than 2 digits for the binary, or 8 digits for the octal and for the hexadecimal, etc. So that's pretty much the idea about it. And yeah, so this is just explaining the same logic. Now if we have this, for example, which is similar to what we did, but it's not the same. So if we have 0 plus 1, that means it's going to give us 1. 1 plus 1, that's 0, and I'm going to carry on the 1 here. 1 plus 1 plus 0, that means it's going to be 0, and then carry on the 1. 1 plus 1 plus 1, that's 3. Okay, 1 plus 1 plus 1, this is an interesting example. So that's 3, right? So because this is 0, 1, 2, 3, which means when I have 1 plus 1 plus 1, I'm going to have 1, and this one I'm going to carry it out here. It's going to be added as well. So that's the same way how we do the calculations with the decimals, except now we're using them for a different base. Is that okay? For the multiplication, it's kind of similar, but it's slightly interesting. Why? Because actually in the multiplication we also included the addition. Now if we multiply, let's say I'm just going to give you like 25. Let me just do that in an easy number. What happened? Again, the bug. Shift F5. If I'm multiplying, let's say I'm going to find two numbers easy with okay, another easy number with 11. So how do we multiply these numbers? If I want to do them manually, let me just go back to here. Okay, if I want to multiply, we said 12 times 11. So what we do, we just take the first one and then we multiply this first one with the rest. That means we have 12, 1, 2, and then when we multiply this one, what we do, I'm going to assume that this is kind of like a 0, right? And then I'm going to multiply this 12, because this is actually 10 multiplied by 2. This is 1 multiplied by 2, 1 multiplied by 1, but here this is 10 multiplied by 2, 10 multiplied by, that's why we keep this 0 here on the right side. So 1 multiplied by 2, that means it's going to be 2, 1 multiplied by 1, that's going to be 1, and then what we do is we do the addition now between these two. So this is going to be 2, 3, 1, so this 12 multiplied by 11 is going to give us 132. This is what we do. Now, just in case I'm doing something wrong, I just would like to make sure that we calculate it right. Okay, let me go back to here, and let's have 12 multiplied by 11. It's 132. This is how we do things. Now, if we work now with binary, it's going to be exactly the same thing. So we have now 3 digits. That means I'm going to leave 3 spaces here. That's the idea behind those spaces. This is like basically like the zeros. Okay, so 1 multiplied by 0, that's going to give me 0. 1 multiplied by 1, that's 1. 1 multiplied by 1, that's 1. So I'll just go here and do the multiplication and put it in the first part. Now I'm going to the second part, so I'm just going to leave here. You can put it as a 0, it's going to be exactly the same thing. And I'm going to multiply 0 times 0, that's 0. 0 times anything actually is going to be zeros. And then I go for the third digit, that means I'm going to leave 2 spaces, and then 1 times 0 is going to be 0. 1 times 1 is 1, 1 times 1 is 1. And all I have to do now is do the pluses. So this plus that. 0 plus 0 plus 0, that's 0. 1 plus 0 plus 0, that's 1. 1 plus 0 plus 0, that's 1. 0 plus 1, and then 1. And that's basically it. So it's the same logic, the same way, except that, again, we just reach the maximum digits that we can use in a base very quickly, especially in the binary. The octal is fairly close, but the hexadecimal actually is the one that takes is actually more than the decimal, so it should be fine. And that's pretty much it for this here. So we have a couple of exercises. So let's do a couple, because just a few ones just to get started, and then I'll let you take the mini test, inshallah, and then we can go for salah, inshallah. So okay, let's pick something. For example, convert the decimal expression to the binary. I'm just going to take the easy one because it will be faster. So if I'd like to convert this to binary, remember what we need to do? So this 231, to convert it to binary, I just need to divide it by 2 plus whatever the quotient is going to be. So 231 is going to be 231 is going to be equal to what? 230, that means 115 plus 1, 115 times 2 plus 1. So this is the first one we have. That means 115 is going to be equal to 57. Again, correct me if I'm wrong. Plus 1. 57 is going to be, now this is 25 plus 3. That's 28 times 2 plus 1. And 28 is equal to 14 times 2 plus 0. 14, that's equal to 7 times 2 plus 1. No, that's plus 0. The 1 is coming up later. And then we have 7 is equal to, I don't know why I write completely in diagonal, but okay. And then I have this 3 is equal to what? 1 times 2 plus 1. And then 1 is equal to 0 times 2 plus 1. And this is going to be my digits, which is this. I need to write from right to left. 1, 1, 1, 0. And then I put a little space, and then I have another 0, 1, 1, 1. So these are the 1, 2, 3, 4, 5, 6, 7, 8. The 8 bits that are going to be the remainder of those. So 1, 1, 1, 0, 0, 1, 1, 1. Let's see, is that right? Yeah, okay, so it just shows us that this is the way how to do it. Now convert these to decimal, but to convert them to decimal, remember what we need to do is just to have these to be zeros, zeros, zeros. Why am I saying zeros? This is position 0, this is position 1, position 2, position 3, position 4, which means this is going to be equal to 1 times 2 to the position 4 plus, no, this is not a, okay, plus 1 times 2 to the position to the power of 3 plus 1 times 2 to the power of 2 plus 1 times 2 to the power of 1 plus 1 times 2 to the power of 0, which is going to be 1 here, which is this whole thing is 1, and then this whole thing is 2, this is 4, this is 8, and this is 16. 16 plus 4, that's 20. 8 plus 2, that's 10. That means there's 30. And there's 1, that means 31. Am I right? Somebody was saying something. 31, good job. Okay, so I'm not going to do all the exercises. I'll let you just practice them, and you have the solutions, so you can find those, some of them. And we also have the sum of these two, and then the multiplication of them. You can also, practice those, inshallah. So I just noticed that I need to start now before, so I can give you some time. Any questions you want me to answer before we start with the quiz? I'm just going to do the same wake up call, ready for the mini test. Let me stop the recording.